Pattern generator circuits use command neurons to control repeated movements. Examples include swimming in fish, worms, and many other organisms, walking, and leg juggling. In these circuits, command neurons control a sequence of movements that go from A to B to C, as many as we want, and then back up to movement A. And as long as the command neuron is stimulated, this whole sequence keeps repeating. So in general in these circuits, often there's a command neuron that stimulates a motor neuron to some muscle for the first movement, and then there's detection of it, which stimulates a motor neuron to muscle B, which again can be detected and can stimulate a motor neuron to muscle C, and so on. Often, an element in these systems is that once muscle A is contracted, the detection also stimulates a neuron that inhibits muscle A. And so muscle A contracts, and when it's finished contracting, action potentials in a sensory neuron stimulate an interneuron that both stimulates the motor neuron for muscle B and stimulates an interneuron that inhibits A. The result is when B contracts, A is being relaxed. So we can get a sequence of muscle contractions and relaxations that cause a particular behavior. So the example I'm going to do is the radula of a mollusk. There would be a belt of collagen with mineralized teeth over some stiff or bony structure with a muscle at both ends. So if muscle A contracts, it pulls the radula this way, and each tooth scrapes across the food in this direction. If this muscle relaxes, muscle A relaxes, and muscle B contracts, then it pulls the radula back in the other direction. So if muscle A and B contract, then alternately the radula is pulled one way and then the other, rasping back and forth. A pattern generator system controls this. So let's sketch the system. Here's A, B, and a radula with teeth. You know there's going to be a command neuron, but we won't connect it to anything yet. You know there has to be a motor neuron that causes action potentials in A, and we'll call it MA. We need a motor neuron that will cause action potentials in B, and we'll call it MB. So the command neuron needs to stimulate an interneuron C to start this process going. So when the command neuron fires an action potential, C will cause an action potential in motor neuron A, which will cause the muscle to contract. And if there's a sensory neuron, D, it can detect that contraction and release neurotransmitter to cause action potentials in motor neuron B to cause action potentials in muscle B. But if both A and B are producing muscle contractions at the same time, the radula won't move. And so E also needs a branch that stimulates interneuron F to inhibit motor neuron A. So now let's run through what our system is going to do, and I'll do it in green. So the command neuron fires an action potential, we get neurotransmitter, and we get an action neurotransmitter released and an action potential in motor neuron A, which causes contraction, which opens stretch channels in D, and so we get an action potential in D, which causes neurotransmitter release to E, and at the same time we stimulate contraction of B and inhibit A. So the result has been we contract A. Once it's contracted, we've pulled the radula up this way, so the radula's been pulled this way. Once it's contracted, that stimulates B to contract. So contraction in B pulls in this direction, pulls the radula back. And once that's completed, that's going to stretch A again, which is going to stop neuron D from producing action potential, which is going to prevent the inhibition of motor neuron A. And as long as the command neuron is still producing action potentials, we'll get action potentials in C and A, and we'll start all over again. So to run through it again, we get an action potential here, which causes contraction. We stretch these stretch channels, which gets an action potential in C and inhibits B. A is going to stop contracting. And at the same time, we stimulate contraction of B. Once B has contracted to a shorter length, that has stretched A back out to its original length. So at that point, because of the stretching, there will no longer be ions moving in the stretch channel. So there will no longer be an action potential here, and this entire part of the pathway stops. We no longer are inhibiting B, so the command neuron, which has still been firing action potentials, now effectively causes action potentials in B, which contracts A and starts the process over again.